Testing, testing. How do I get the doggone link? Testing, testing, 1, 2. Testing, 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 testing. Can you hear me? Okay. Check page 157. And okay. Okay. Sorry. So this is chapter 9, page 157 of Mechanical Ventilator Graphics. Volume control ventilation with varying gas flow waveforms. Chapter 6 various flow patterns available during volume control ventilation and mentioned the benefits of the descending ramp. Figure 911 shows a constant descending flow and a sine flow waveform with accompanying pressure scalars. Although other waveforms are available, they are not common. These are characteristics of volume ventilation with any fixed flow pattern, descending other than the constant pattern. Constant rectangular pattern. The flow waveform provided, regardless of type, does not change shape during inspiration, even with changes in lung characteristics. Second bullet, the flow waveform remains the same from breath to breath. Third bullet, volume delivery remains constant as long as the breath is volume cycled. And bullet point 4, pressure patterns measured at the upper with changes in C1 and raw and type of flow pattern selected. Figure 912 illustrates VC-SIMB from a positive baseline. VC-SIMB plus CPAP. Some clinicians refer to this as VC-SIMB with peak. Mandatory breaths are the same as those already discussed. The differences in this case is the occurrence of spontaneous breaths. What happens to the pressure when the patient breathes spontaneous? Look at the flow curve. As the patient breathes spontaneous, the flow rises. Exhales, the flow drops below baseline, just as exhale flow does with a mandatory breath. Volume delivery for spontaneous breaths can vary. Key points of volume control ventilation graphics. Thus far, we have discussed VC-CMV, the constant flow. Key parts of this section include the following. Observing PIP. Hold on one second, I gotta zoom in. Observing PIP, P plateau, and not sure what that is. P and P on the pressure time scalars. Flow time scalars locating the beginning of inspiration, the set flow, the beginning of exhalation, peak expiratory flow, end expiratory flow, and the end of exhalation. Third bullet, calculating compliance from pressure, flow, and flow curves. Fourth bullet, observing inspiratory flow of 0 during inspiratory pause. Fifth bullet, evaluating changes in raw using PTA and the expiratory flow curve. Sixth bullet, increased flow with patient demand on a servo ventilator. Seventh bullet, inadequate sensitivity and inadequate flow and resulting changes in the pressure time curve. Eighth bullet, checking for the presence of auto-PEEP using the expiratory flow curve. Ninth bullet, measuring and observing auto-PEEP levels on the pressure time curve. 10th bullet, checking for leaks and for active exhalation and transducer errors in volume time curves. 12th bullet, different flow patterns during volume controlled ventilation. And 13th bullet, VC-SIMB with CPAP. Completed this section, readers should take the opportunity to observe a patient receiving volume control ventilation and study the available graphics. Following questions can serve as a guide. What is the flow pattern? What is the PEFR? Is auto-PEEP present? Is a leak present? What is the PIP? Is flow to the patient adequate? Has the sensitivity been set appropriately? Okay, and in figure 9-11 says standard mechanical ventilator flow pattern. Constant, descending, and sinusoidal. The effect of the flow pattern on development of pressure is also shown. Eight. These concepts are sometimes better understood when they are observed at the bedside. Repeated study of graphics displays can help make the concepts discussed in this section easier to use and remember. Repeated study of the graphics displays can help make the concepts discussed in this section easier to use and remember. We might want to pressure controlled ventilation. During pressure controlled ventilation, PC-CMV, the clinician sets a pressure to be delivered to the patient's lungs. Flow and tidal volume vary as the patient's lung compliance and airway resistance change. The ventilator attempts to deliver the set pressure at the start of inspiration and maintain the set pressure until expiration begins, producing a nearly constant pressure waveform. Ventilation with a constant pressure waveform. Pressure ventilation with a constant pressure waveform has four important characteristics. One, the pressure waveform is rectangular or constant. The waveform is not affected by change in lung characteristics or patient flow demand. Three, the rate of flow delivery varies with changes in the patient's lung characteristics, set pressure, and inspiratory effect. Four, the flow waveform rises rapidly at the beginning of inspiration and then decreases during inspiration. Continuously variable decelerating pattern. 13, which I will discuss at the end of this page, shows scalars obtained with pressure ventilation. Ventilators operating in pressure ventilation modes, CMV and PSV, deliver constant pressure breaths. Inspiration is time cycled in PC-CMV. Figure 913A shows scalars for a long inspiration time, T1. Flow drops to 0 before the end of the set inspiration time. The pressure and volume scalars show an end inspiratory plateau. This means that the pressure set by the operator and the lung pressure achieved are the same at end inspiration, key point 9-2. No, according to current practices, this pressure should be less than 30 centimeters of H2O water. The greatest volume delivered to the patient for a set pressure is achieved when the pressure from the ventilator has time to equilibrate with the pressure in the lungs. 9-2. When flow drops to 0 at the end of inspiration, an inspiratory pause is present. When flow is 0, the pressure gradient between the ventilator and the patient's lungs is the same. The scalars in figure 9-13B show a shorter T1. When T1 is short, the P does not reach set pressure, P alv, I think that says, does not reach the set. No plateau pattern is seen in the pressure and volume curves. Inspiratory flow ends abruptly without gradually decreasing to 0. Notice that in this example, the delivered volume is slightly decreased because not all the set pressure is delivered to the lungs. The pressure in the lungs normally is equal to ambient pressure at the start of inspiration. When the ventilator starts inspiration, the P-alv rises rapidly because the pressure gradient between ventilator and the lung is at its highest. As a result, gas flow from the ventilator also is at its greatest level. See figure 5-3. Gas passes through conductive airways and enters the lungs. As the lungs fill with the air, P-alv rises and approaches the set pressure. The closer the P-alv and ventilator pressures are, the smaller the pressure gradient, the smaller the rate of gas flow decreases. Well, almost in the page 158. Figure 9-12 says VC-SIMD plus CPAP / P. See text for explanation. And shows the flow, pressure, and volume. Wait, I believe those are waveforms. Okay. Next page. Pressures in the lung and the ventilator finally equilibrate. Flow drops to 0. See figure 9-13A. The resulting flow waveform is called a continuously variable decelerating waveform. The volume of gas in the lungs at any point in the cycle equals the product of C1 and P-alv. The rate of volume filling is rapid at the beginning of inspiration, decreases toward the end of inspiration. It is important to recognize that the pressure required to overcome airway resistance is greatest at the beginning of inspiration when flow is highest. PTA, therefore, is high at the beginning of inspiration. As flow decreases during raw is constant, the pressure required to overcome airway resistance, or PTA, decreases throughout inspiration. At the end, flow stops, there is no resistance, PTA equals 0. Okay. It's titled Comparison of Pressure Controlled Ventilation and Volume Controlled Ventilation. When pressure and volume breaths are compared, the pressure and flow curve demonstrates the most distinct differences. Volume controlled ventilation with constant flow produces a rectangular flow curve, which can be changed by selecting a different flow waveform. Controlled ventilation, the flow waveform is a descending curve that varies with both lung characteristics and patient flow demand. It therefore is referred to as a continuously variable decelerating waveform. During volume-controlled ventilation, the pressure curve resembles an ascending ramp or a rising exponential curve. During pressure-controlled ventilation, it is rectangular, assuming T1 is long enough. During volume-controlled ventilation, the pressure waveform varies with changes in lung characteristics. For example, static compliance, C and raw. I can't quite see that. With pressure ventilation, changes in it's a C5 or no CS, and raw change flow and volume delivery, but the pressure waveform remains the same. Figure 914 shows how increased raw changes the appearance of the flow curve shown in figure 913. Notice in figure 913, the increased resistance is the result of the reduction in small airway. Okay. Okay. Let me go back to that last paragraph. Column 1, page 159. It says figure 914 shows how increased raw changes the appearance of flow curve shown in figure 913A. Notice in figure 914, the increased resistance is the result of a reduction in small airway diameter. This can occur with conditions such as COPD or severe asthma. Again, the highest point of the pressure gradient between the ventilator and the lungs occurs at the start of inspiration, figure 914A. Because of this increased resistance, the pressure does not reach the alveolar levels as easily, figure 914B. Therefore, the pressure gradient, delta P, remains high throughout inspiration, figure 914, C and D. Rather than dropping rapidly with increased raw, the flow curve assumes a flatter appearance. If the flow does not drop to 0 by the time the set T1 elapses, the ventilator and lung pressures will not equilibrate. This can affect overall volume delivery. See figures 914C and D. In compliance during pressure controlled continuous mechanical ventilation. Figure 915A illustrates volume delivery during PCCMV with normal compliance or resistance. PCMV compliance is reduced by half and the volume delivered is reduced by 50%. In figure 915C, the resistance is increased to twice that in figure 915A. As a result, volume delivery is less in figure 915C than in figure 9-15A. These illustrations demonstrate the scalar changes that can be expected with PC/CMV with changes in compliance and resistance. Next section, active inspiration and expiration. In figure 916, the solid line in all scalars represents a typical patient-triggered, pressure-targeted, time-cycled breath. The dashed line shown in the flow and volume scalars represents active inspiration, volume and flow delivery. The patient can receive additional flow during pressure ventilation with increased effort. The function of the ventilator is to maintain a set pressure regardless of patient demand for flow. Inspiratory rise time controls sloping or ramping. A pressure breath produces a high flow at the beginning of inspiration with small diameter ET. For example, increased raw. The high flow through the narrow opening creates turbulence. As a result, a pressure overshoot can occur at the beginning of the pressure curve before the pressure adjusts to the set value. Okay, and page 159. Give me just 1 second. Okay, I forgot I gotta read these captions. Okay, figure 9-13A will show, it says PCCMV scalars for pressure bottom, volume middle, and flow top during PC-CMV. They long T1 becomes equal to the peak or set pressure because flow returns to 0 before the end of the inspiration. B, T1 is shorter. Flow does not return to 0, nor is an inflation hold during inspiration. See text for explanation. Okay, next page, 160. I'm going to save a figure in the case study till the end. Okay. If the flow and pressure delivery are tapered at the start of the inspiration, the waveform can be adjusted to reduce this overshoot. Acute care ventilators have a function that can taper the flow during pressure ventilation. When tapering is used, the pressure curve may no longer be constant, but may be tapered at the beginning of the breath. Inspiratory flow delivery during the PC-CMV therefore can be adjusted with an inspiratory rise time control, also called a slope control. Figure 917. Table 9-1 lists the names given to this control on different ventilators. The sloping or inspiratory rise time function controls the rate at which the flow valve opens. Adjusting the inspiratory rise time can either reduce or increase the rate at which pressure and flow exit the ventilators for a specific period. Are most apparent on the pressure and flow scalars. Adjusting the flow delivery at the beginning of the breath may be more comfortable for the patient. It may also serve as a way to breath delivery with patient flow demand, improve patient ventilator synchrony, and reduce the work of breathing, or WOB. However, adjustment of the rise time must be done with caution because too much tapering of flow and pressure delivery can reduce the VT and cause patient ventilator asynchrony. Figure 917 shows a series of rise time slope settings, 2, 4, 6, 8, -10, and 12. During the first breath, very little sloping is used. The flow valve is delivering flow that is adequate for patient demand. The pressure ramp rises and has a linear shape. During the second breath, sloping has tapered flow and pressure, but patient demand is still met. During the third and fourth breaths, too much sloping is used. The flow valve opens too slowly to meet patient demand, resulting in a convex pressure trace, inadequate patient flow. Use thus volume delivery. In general, an excessive initial flow has only minor effects in insufficient initial flow. On the other hand, can have more serious consequences. Case study exercise 9.2. Rise time adjustment generally is limited to pressure targeted ventilation, PC-CMV, and PSV, although the Servo by McKay also can slope volume targeted breaths. The inspiratory rise time, or sloping, feature is described in more detail in the section on pressure support. Pressure control, SIMV. I'm busy, I'm working. Pressure controlled SIMV plus CPAP, figure 918 presents scalars from PC SIMV plus CPAP and PSV with pressure targeted mandatory breaths with spontaneous breathing at a positive baseline pressure. Note that the volume for the first spontaneous breath is greater than the second spontaneous breath. Pressure controlled ventilation graphics. This section discusses the following topics: pressure, volume, and flow scalars with PC-CMV, pressure controlled ventilation graphics, I believe, ventilation with long T1 and short. Okay, long T1 and short T1. In flow waveform during PC-CMV with normal airways and with increased airway resistance, changes in volume delivery in PC-CMV with normal CS, half normal CS, and twice normal raw. The next point is active inspiration compared with a time-triggered breath, pressure scalar. Next point is inspiratory rise time or sloping in pressure targeted ventilation. And the last bullet is PC-SIMV plus CPAP and PSV. Okay, let me go over figure 9 and case study. 914, patient with increased raw ventilated with PC-CMV. The set pressure is 25 centimeters of water. Section A, at the beginning of the breath, the pressure gradient is delta P, or change in P, which is 25 centimeters of water. And it says set P minus P-AL. In section B, it says P-AL is 5 centimeters of water. Change in P for pressure, I believe, is 20 centimeters of water. Section C says P-AL is 10 centimeters of water, 15 centimeters of water. Section D, P-AL is 15 centimeters of water. Delta P is 10 centimeters of water. inspiration is not as rapid as normal raw. Flow does not reach zero by end inspiration. Volume delivery is lower than the normal raw. Okay, the case study says 9-2. Problem solving in PCCMB. A patient diagnosed with PS is placed on PC-CMB at the following setting. PEEP equals 10 centimeters of water. O2 equals 0.8. Set pressure equals 18 centimeters of water. PIP equals 28 centimeters of water. VT equals 350 milliliters, down from 450 milliliters. At the slowest possible flow delivery. Arterial pressure gas, or ABG levels, on these flow settings are as follows. 7.28. PaCO2 equals 49, an increase of 9 millimeters Hg. PaO2 equals 53 millimeters Hg, down from 68 millimeters Hg. The respiratory therapist notices that PIP reaches only 23 centimeters of water. No leak is found in the system. What recommendations could you offer to improve this patient's ABG, or arterial blood gas? So see Appendix A. Okay. 1 second. Gotta zoom in. And next page, 161. Later graphics, I'll again read the. This next section is called pressure support ventilation. Pressure support ventilation, PSV, is a patient-triggered pressure-targeted flow cycle mode of ventilation. See figure 5.7 for common flow, pressure, and volume scalage for PSV. A slight negative deflection in the pressure curve occurs before each breath, reflecting the patient's inspiratory effort. Every breath is patient-triggered. As lung characteristics deteriorate, pressure remains constant, but the delivered volume may decrease. If the patient effort decreases, the delivered volume also increases. In the addition to the set pressure and the sensitivity, this can be set with PSV. The inspiratory rise time or slope, as described with PC-CMB, and the inspiratory flow cycle value, also called the flow cycle percent. Okay, details of the pressure time waveform in pressure support ventilation. Figure 9-19 shows a pressure time waveform for PS breath. Example of an appropriate sensitivity setting. When pressure time, or PT curve, the clinician must always ensure that the sensitivity setting is appropriate for the patient so as not to make it too difficult for the patient to trigger the breath. Figure 919-line A illustrates an appropriate sensitivity setting. This is the rapid rise in pressure represented by the solid line, point B2-A. Demonstrates a slope or rise time set so that the increase to the set pressure is tapered. The set pressure is C. The arrow labeled 1, top left, shows an overshoot in the pressure curve. As described earlier, this overshoot is associated with turbulent airflow, which is created when the delivered pressure encounters a small ET airway. An overshoot may also indicate that flow exceeds patient demand. The overshoot. The pressure drops to its set value. Respiratory rise time slope can eliminate this artifact by limiting the maximum available flow. Figure 915 states theoretical waveforms generated by a microprocessor-controlled ventilator operating mode for pressure ventilation. pressure setting is 10 centimeters of water. Inspiratory time is 1.5 seconds. Compliance is 50 milliliters per centimeter of water. And airway resistance is 6 centimeters of water per liter per second. Standard conditions described, section B, compliance has been halved, 25 milliliters per centimeter of water. C, airway resistance has doubled, 12 centimeters of water per liter per second. End of page. Okay. Give me a second. Zoom in. I will read two figures 916 and 917. And page 162. Cycle percent, discussed later in the chapter. Inspiratory inspiration ends, the pressure drops to the baseline pressure, represented by the solid line in figure 919. Reduction in pressure, D1, arrow upper right, in this curve illustrates another problem that can occur with PS. What could cause the pressure to increase, as indicated by the dashed line? Where is a constant pressure, therefore it is not the ventilator. The increase shows active exhalation by patient trying to end. The finding, which is referred to as delayed termination, is associated with patient ventilator asynchronous. Delayed termination is often seen during PS with patients who have COPD that increases raw. The ventilator can be adjusted to shorten T1 and lengthen T1. During PSV, see the following section on flow cycling. The dashed line, B2, in figure 919 represents a rapid drop in pressure at the end of inspiration and the beginning of exhalation. This can occur when automatic tube compensation, or ATC, is used to assist exhalation. ATC is a ventilator feature that helps compensate for the work of breathing WOP imposed by the ET. ATC augments flow during inspiration. Some ventilators, for example, the Draeger E2, can compensate for expiratory work through the ET during expiration by providing a slight pressure gradient between the lungs and upper airway, facilitating exhalation. ATC is discussed in more pressure is discussed in more detail in chapter 20. Okay, next section. Flow cycling during pressure support ventilation. The normal flow cycling mechanism of PSV was discussed in chapter 3 and 5. Flow cycling occurs when the ventilator detects increasing flow, end of inspiration. The ventilator software determines the point at which flow cycling occurs. In most ventilators, this point is a percentage of the flow measured during inspiration. Table 9.1 presents the flow cycle variables for a variety of ventilators. Hold on one moment. Okay. Okay, I'll take a little 2-minute pause. Okay, grab a drink with that. Just don't think nothing else. All right. Okay. Um, okay. Slow cycling, slow cycling during pressure support ventilation. The normal flow cycling mechanism of the PSD was discussed in chapter 3 and 5. Flow cycling occurs when the ventilator detects a decreasing flow, which represents the end of inspiration. The ventilator software determines the point at which flow cycling occurs. In most ventilators, this point is a percentage of the peak flow measured during inspiration. Table 9.1 presents the flow cycle variables for a variety of ventilators. Unfortunately, no single flow cycle percent is ideal for all patients. Patients with COPD or increased RAW have a slower flow rate drop off than with pressure ventilation than do patients with normal RAW. See figure 9.14. Because the flow does not drop, normally patients with COPD are more comfortable with a higher flow cycle percent, e.g. 40%. Clinicians can determine the appropriate cycling criteria by evaluating the PT curve during PSV. If the active rise in pressure occurs at inspiration, the flow cycle percent may be increased to reduce the amount of expiratory flow formed. The graphics in figure 920 show two flow per cycle percentages. What is the peak flow in A value, where inspiratory flow ends? What is the approximate flow cycle percentage? What is the peak flow in B? What is the flow cycle where inspiratory flow ends? What is the approximate flow cycle percentage in B? In conditions marked by reduced C1, fibrosis, the lungs fill quickly during pressure ventilation, but do not fill with as much volume. Also empty quickly. For patients with stiff lungs to gain the most benefit, the breath must last longer. In such cases, the flow cycle percent is set to a low value where 10%, excuse me, in such cases, the flow cycle percent is set to a low value, example 10%, to increase the duration of the breath. This allows the patient to gain as much volume as possible for the set pressure. Of the flow cycle criterion. Adjusting the flow cycle criterion during PSV is difficult because lung mechanics, or CS, and RAW may change frequently. One approach to solving this problem involves using a software program that analyzes raw time constant for each patient breath. Okay, I'm going to go back and read the figures. Okay. Okay, figure 916 represents the flow, pressure, and volume scalars for PCCMB. The dashed line represents active inspiration by the patient. Increase in volume and flow delivery. Pressure T1 remains unchanged. Changes in the gas delivery system produced by adjusting the pressure, slope, or rise time function. Ventilation. See text for additional information. Okay. Let's see what we got next. Names and settings, respiratory rise time, and flow cycle on various ventilators. Do you want me to read out the information in Table 9? Jamon? Okay. See to that page. At the end, page 165. Okay. Page 165, page 165. Program also analyzes the slope form at the end of inspiration, last 80 milliseconds, associated with active breathing, 0.8 or 0.8 centimeter, of which would suggest cycle asynchrony ventilation. In this situation, the ventilator would use a higher flow cycle criterion for the next breath. Rise at the end of the inspiratory flow, the inspiratory time is less than 0.2 centimeters of water, which suggests no active exhalation. The flow cycle criterion is reduced by 5%. Was first introduced by Newport Medical for worldwide distribution outside the United States in 2001 as flex cycle on Newport E500 ventilator, and subsequently added to the Newport E360 ventilator in 2006. It was added to the Newport E ventilator for use in the United States. Flex cycle uses pulmonary time constants calculated at an exhalation waveform and inspiration to adjust flow cycle off threshold automatically to suit the patient's specific needs. The processor makes these adjustments on a breath-by-breath basis, although feature and requires additional research. Automatic selection cycle may prove to be a valuable tool for adjusting PS. Hold on one second. Okay. Use of ventilation with SIMV. 21 scalars SIMV plus PSV and CPAP. For spontaneous PS, breaths are lower than those for mandatory breaths. Spontaneous breaths can be distinguished from mandatory breaths. Here for the PS breaths and figure 921 0. Volume delivery breaths can vary. Pressure volume loops. Pressure volume, PV loops can be used to monitor changes in lung compliance. Delta V divided by delta P. Component of the pressure volume loop. Figure 922 shows a typical P generated during a positive pressure breath. Breath is time ventilator triggered. Trigger when the ventilator provides a breath, the loop is drawn in a counterclockwise direction. Notice that the inspiratory and expiratory curves are not perfect. Okay. Also note that the maximum pressure reached on the x-axis is the PIP, and the maximum volume reached on the y-axis is the solid line of the loop in figure 923 represents and volume. The dashed line represents the static L under no flow conditions. I can't tell P A or flow resistance pressure, which is the difference between the PL. Yes, I am. O represented by a double-headed arrow, and the values BT, PTA, and PPL, and PV loop shown in 3. Pressure group volume loop with changes in flow. delivery can alter the P loop for higher flows result in higher PTA. PTA divided by flow. The inflow increases, the PTA will, for example, if raw is 2 centimeters, 2 centimeters of water per liter, flow is 0 liters per second, 60 PTA is 2.0 centimeters of water. What is the PTA if raw is 2 centimeters of water and flow drops 5 liters per second, which is 30 liters per minute? It says PTA is 1 centimeter of water.